So in last video, we saw how to model coils that are tightly coupled. So we have two coils, L1, L2, and assuming they are ideally coupled, we mentioned that if we have a voltage on the primary side, it will be transferred to the secondary side according to the turns ratio of the two transformers. So basically it will be N2 over N1 times V1. And similarly, if we have input current I1, it will be transferred to the secondary side with the reciprocal ratio, so N1 over N2 times I1. And also we mentioned that if we have an impedance on the secondary side, for example, it will be seen on the primary side basically as N1 over N2 square times Z2, which means that the ratio between the impedances will be the voltage transfer ratio squared. Okay, so an ideal transformer essentially is a model for tightly coupled transformers. Essentially, state three facts or mainly two facts. The is that essentially as a transformer couples the voltage from the primary to the secondary according to the turns ratio N2 over N1, and the current according to the reciprocal ratio N1 over N2, and then we will have impedance transformation ratio that's equal to the voltage transfer ratio squared. However, for a wireless power transfer system, the coils are not tightly coupled. Essentially, the distance between the coils could be large, relatively large to their diameter, as well as the orientation of one coil with respect to the other might not be in the perfect position or perfect orientation. And so in this case, the simple models that we have, just to N1, N2, V1, V2, I1, I2. The simple models that we have for tightly coupled coils doesn't apply, and we need to modify it to add some parasitic elements that essentially models the weak coupling between the primary and secondary coils. Okay, so we will take this ideal model or the model for tightly coupled coils, and we're going to add some parasitic elements that basically model the weak coupling that happens between the primary and secondary of loosely coupled coils. Now, just a side note, this model for tightly coupled coils, one question that comes to mind is, when is it applicable? Like, is there actually practical cases where the coils are tightly coupled? And the answer is yes. In power transformers, you'll find the primary and secondary coils are tightly coupled. Essentially, you will see that one coil is wound on the same ferrite core or core material essentially as L2, and this ferrite core is going to align the magnetic field that's produced by, say, the primary, and make all of the magnetic field produced by the primary to couple to the secondary coil. So essentially it aligns the coupling. It enables the two coils to achieve almost ideal coupling or perfect coupling, magnetic coupling. And if we open this transformer, we see that basically it's two coils that are wound on the same core material, And as I mentioned, this maximizes the coupling between the two coils, and so we can use the simple model that we had last video for tightly coupled coils. Also, there are about 3 different structures for a power transformer. One structure is where the two coils, primary and secondary, are wound on the same on a ferrite or magnetic core, essentially to maximize the coupling between them. There's also another structure is to basically wound the secondary coil on top of the primary coil. And of course we have the magnetic core essentially is surrounding both in the middle as well as in the surrounding of both coils as shown in this figure. One question of course here is wouldn't the wires get shorted? Well, typically the copper wires of which the coils are made are basically insulated by a wax material, and this wax material will stop conducting or essentially shorting the wires together. Another or a third structure is the U shape essentially for a power transformer, where both the primary and secondary are wound on the same core material, and so essentially the magnetic field is basically being transferred across the core material, and the core material essentially maximizes the coupling between the primary and secondary coil. So for all these 3 types of transformer, or basically power transformers, the coupling between the primary and secondary coils is maximized by using a core or ferromagnetic material that basically aligns the magnetic fields produced by one coil to couple with the other coil. Now, let's look at loosely coupled coils. So first of all, for loosely coupled coil, we know that any coil has an equivalent self-inductance, right? Before considering the weak couplings that happen between the primary and secondary, we know that any coil you have is going to have its own self-inductance. Let's say this coil is going to have L1 inductance. The secondary coil, in its own, if we measure its equivalent inductance, it will be, say, L2. Okay, so each coil alone, without putting them near each other, has its own self-inductance. Now, how to model that using circuit elements? So what we are going to do, we're going to introduce what's called ideal transformer model. An ideal transformer model is basically is given by this symbol, and basically it signifies 2 equations that you have primary and secondary coils of N1 to N2 turns ratio. That if you have voltage V1 on the primary, it will be coupled or transferred to the secondary according to the ratio V2 over V1 equal to the turns ratio N2 over N1, or which is called N small. By the way, we mentioned last video that N2 over N1 is equal to L2 over the square root of L2 over L1. The second equation that this symbol for an ideal transformer indicates is that the ratio between the current at the secondary and the current at the primary, so I2 over I1, is going to be equal to the reciprocal ratio, or the reciprocal of the voltage conversion ratio, so N1 over N2, or basically 1 over N. Okay, so again, we introduced in this video basically what's called ideal transformer model. It has the symbol shown here, and basically it indicates 2 mathematical equations that V2 on the secondary to V1 on the primary is equal to the turns ratio N2 over N1, or square root to L2 over L1. Number 2 is the ratio between the currents I2 over I1 is the reciprocal of the voltage conversion ratio, so N1 over N2, which is equal to 1 over N small. Okay, so we have this ideal transformer model. Now, as I mentioned, if we take the primary coil, the physical primary coil, and we measure its inductance alone, we'll find it to have its own self-inductance. And the same thing for the secondary coil, it has its own self-inductance. So what we are going to do in order to account for that in the transformer model, we're going to use the ideal transformer model of certain turns ratio N1 to N2, the turns ratio of the primary, and and the number of turns of the secondary coil. And we're going to add the self-inductance of the primary coil in order to model this self-inductance of L1. Okay, and in this case, should we add also the self-inductance of the secondary coil? Well, the answer is no. Because if we look at the impedance or the inductance we will measure if we look into the secondary side, we'll find it is equal to what? It's going to be N2 over N1 squared multiplied by L1. We said that N2 over N1, the turns ratio is basically equal to square root L2 over L1. So N2 over N1 squared is going to be equal to L2 over L1 multiplied by L1, which is equal to L2. So essentially, by just adding the self-inductance of the primary coil on the primary side as shown here, essentially we also modeled the self-inductance that we will see on the secondary side, or basically the primary side inductance or L1 will be seen as L2 from the secondary side, so there is no need to add another inductance L2 on the secondary side. We can also equivalently, if this is the ideal transformer, we can also just model the self-inductances of the primary and secondary by one inductance L2 on the secondary. And again, the reason is because this inductance will be seen from the primary side as L1. Okay, so that's the first point, is modeling the self-inductances of the primary coil and the secondary coil. And one reason that I'll come back to this point later on in this video is that why we didn't consider these self-inductances in a power transformer. And the reason is the value of these self-inductances is extremely large or very high in a power transformer, that basically they behave as an open circuit, because the equivalent reactance of this inductance is going to be J omega L1. And if L1 is very large, this essentially means this reactance or impedance will approach infinity, so we can ignore it or essentially replace it by an open circuit. However, in a resonant wireless power transfer system, we'll find that the self-inductances of the primary and secondary coil, or the transmitting and the receiving coil, is basically small. So we need to take them into account. Okay. Now, what is the effect of the inductances, the self-inductances L1 and L2? And again, when we represent L1 and L2 using our ideal transformer model, we just need to add one inductance L1 on the primary second or L2 on the secondary side. We don't need to add both L1 and L2, the self-inductances on the primary and the secondary. Because essentially, if we add L1, as I just mentioned, on the primary, it will be seen as L2 from the secondary, and if we add L2 in the secondary, we'll see it as L1 from the primary. So it's enough to add just one self-inductance, either for L1 or for L2. Now, what is the effect of the self-inductance? Well, you can imagine the wireless power transfer system, if this is the voltage that's applied, the AC voltage that's applied, basically, it will cause current flowing into the self-inductance. So it will have an amplitude V capital 1, the amplitude of the input sinusoidal voltage divided by J omega L1. And so in addition to the current that's flowing to the useful load, the load that we are building this power transfer system in order to power or essentially charge the output battery, in addition to this useful current, we have additional current that's flowing in the self-inductance of the coil. Okay, and this basically will increase the current that's taken from the source. Okay, in as I just mentioned in power transformers, within in tightly coupled transformers that basically represent power transformers, we find that L1 and L2 are basically very large in value. So basically, we can ignore this current because J omega L1, the reactance, is extremely large in value. On the other hand, as I mentioned, in wireless power transfer system or loosely coupled coils, we'll find that L1 and L2 are basically small, and this will cause extra loading. So in order to avoid this extra current that's flowing in the self-inductance of L1 or self-inductance of L2, if we represent that self-inductance by L2 in the secondary side, in order to avoid this extra current in the source or increasing the current in the source driving the transmitter, what we do, we add a capacitance C1 in order to cancel the self-inductance L1 on the primary side. And I'll get to this point later on in detail in a following video. Okay, but all I want you to know right now, the self-inductance of the transmitting and receiving coils in a wireless power transfer system is small in value, which causes basically loading on the source driving the wireless power transfer system. And so we need to add a series capacitance to tune out this inductance and avoid this self-inductance and avoid this extra current in the source. Now, from the word loosely coupled coil, the coupling between L1 and L2 is going to be weak. So essentially, in a power transformer, since we have magnetic core, all of the flux, magnetic flux that's generated by L1, the primary side, will be coupled to the secondary side. Okay, and that's thanks to using a core material. This two parallel lines represent there is a core material. And this magnetic core material is going to align the flux such that all of the flux produced by the primary is going to couple or go through the secondary side. However, in loosely coupled coils, we'll find that due to the distance or not so perfect orientation, the magnetic flux that's produced by the primary, not all of the magnetic flux produced by the primary is going to reach the secondary. So some of the flux will not reach the secondary side, and we call this phi 11. And the flux that reaches the magnetic flux that reaches the secondary as phi 2 from 1. So due to this lost flux or loosely what we call it weak linkage between the primary or transmitting and receiving coils, due to this phi 11, we'll find that not all of the voltage applied on the primary is going to reach the secondary. So here, in the case of using or tightly coupled magnetic cores, we'll find that all of V1, assuming we have 1-to-1 turns ratio, say, so N1 and N2 is equal to each other, we'll find that in tightly coupled coils, all of V1 is going to appear across the secondary. On the other hand, in loosely coupled coils, due to this flux that doesn't couple or linkage with the secondary coil, we'll find that the voltage produced on the secondary side is going to be less than V1. Okay. So how do we model this in our ideal transformer or using an ideal transformer? Well, since basically the voltage that appears on the secondary side is going to be lower in value than the voltage applied at the primary, okay, assuming N1 is equal to N2 for simplicity, then we can model this loss in flux by adding a series inductance, this inductance, with the self-inductance L1 that we introduced in a prior slide. And the reason we add this series inductance, and let's call it L leakage, is that it's going to introduce voltage drop. So V1 will be divided between the leakage inductance as well as L1. And so the voltage that will be produced across the secondary side is going to be less than V1, assuming N1 is equal to N2 for simplicity. Okay, and the same thing will happen if N1 is not equal to N2. We just add a leakage inductance so that we establish a voltage divider that basically will reduce the voltage that's the amplitude of the voltage that's applied across the ideal transformer, and as a result the voltage that will appear on the secondary side will be less than its ideal value, or essentially the case when all of the primary, the flux that's produced by the primary is linking with the secondary coil. Okay, so now the question is, what is the value of this leakage inductance? Well, typically this leakage inductance we represented by L1 as well, as a factor or as a value that's proportional to the self-inductance of the primary coil. And then we multiply that by 1 minus K, where K is a number between 0 and 1. So if K, by the way, is called the coupling, the transformer coupling factor, so basically if the coupling between the primary and secondary is perfect and there is no flux that's lost and all of the flux that's produced by the primary side reaches the secondary side, in this case K is going to be equal to 1. So basically what will happen, this series leakage inductance will approach 0. On the other hand, if there is no linkage, or essentially as the as more and more of the flux that's produced by the primary side essentially doesn't link with the secondary side as phi 11 increases, what will happen basically is the coupling factor K is going to decrease from 1 towards 0, depending on how much flux is lost and is not linking with the secondary side. And so as K is decreasing in value, what will happen is the series inductance, the series leakage inductance essentially is going to what? The series inductance essentially is going to approach L1 value, okay? And essentially is going to increase in value, which is going to essentially reduce the voltage that's produced across the primary side. Now, there's one issue in this simple model. If this is going to be represented as 1 minus K times L1, right? If we left the secondary side open circuit, we don't connect anything on the secondary side, and we try to measure the inductance, the total inductance we see on the primary side, what we should see is, we should see ideally, or the correct values that we should see is the self-inductance of the primary side. However, according to this electrical model, what we are going to see is 1 minus K, the leakage inductance, in series with L1, because essentially this is left open, so I2 is going to be 0, this will also I1 is, or the current here is going to be 0, and so essentially we will see this inductance in series with this inductance. So we have 1 minus K L1 time, in addition to L1, which is equal to 2 minus K times L1, which is not correct. So what we are going to do is to fix this electrical or equivalent model. We're going to represent the parallel inductance as K times L1. And in this way, when we measure the self-inductance, assuming the secondary side is open circuit, what we are going to see is 1 minus K times L1, which is the leakage inductance, in series with K times L1. And so K will cancel this, and we end up with L1, which is the correct thing that we should have, or physically have, if we measure the self-inductance or the inductance of the primary side, assuming V2 is open circuit. Now, another point here is, if this KL1, let's first a little bit of terminology. So this parallel inductance is called the magnetizing inductance, because this is a useful inductance, or this inductance represents the amount of the primary side voltage that will be coupled to the secondary side. That's why it's called magnetizing inductance. On the other hand, this series inductance, as I mentioned, is called leakage inductance, because it represents the flux leakage, the flux that's produced by the primary coil that doesn't link with the secondary coil, say phi11. Okay, so we have magnetizing inductance, the parallel one. This is a useful inductance. The larger its value, the better, because it's going to essentially represent most of or higher fraction of the input voltage is reaching the secondary side. Leakage inductance, on the other hand, we want it to be as small as possible in order to reduce the voltage division effect and deliver a larger fraction of V1 or a larger portion of V1 to the secondary side. Okay, and now the coupling factor of the transformer K, as I mentioned, ranges between 0 and 1. Okay, and so when the coupling factor is equal to 1, so it's perfect coupling, as say in a power transformer, we'll find this series inductance will be essentially 0, which means it is acting as a short circuit, and all of the primary voltage will reach the primary side of the ideal transformer, and so it will reach the secondary side. On the other hand, if K approaches 0, as in the case of loosely coupled coils, we'll find that all of the series inductance will approach L1, while this KL1 will approach 0. So basically, none of the primary side voltage reaches the secondary side. And that makes sense because all of the flux that's produced by the transmitter or primary side is self-coupling rather than linking the secondary side. Okay. Now, there is a small issue here, mathematical issue in this equivalent model. If we look at the inductance that we see from the secondary side, according to this model, assuming we leave the primary side open circuit, what we're going to see, as I mentioned, is N2 over N1 squared times this inductance, which is K times L1. And we mentioned that N2 over N1 is going to be equal to L2 over L1 times K L1. So essentially the inductance we will see in here is what? K L2. So if we leave the primary side open and we measure the inductance here, according to this mathematical or this electrical model, what we're going to find in the multimeter or the equipment that measure inductance, LCR meter for example, LCR meter. Essentially what we're going to see is KL2 instead of L2. We should see L2, the self-inductance of the secondary coil, but we're going to see KL2. So this model need to be, this equivalent circuit or equivalent model need to be modified. And to fix that, what we're going to do is we're going to add another inductance here, another leakage inductance, and the value of this leakage inductance is 1 minus K times L2. In this way, if we do the math, we'll see that the inductance that we will see across the secondary side when we leave the primary side open circuit will be basically equal to L2, the self-inductance of the secondary side, which is the physical value that we will actually measure. All right? Finally, as we know, any coil is going to, assuming the wireless power transfer, this is a transmitting coil L1 and this is a receiving coil L2. These coils are made of copper wires, and these copper wires will have an equivalent series resistance, right? So we'll have R1 and R2. So basically we need to add these to the models. So starting with the ideal transformer, so this is the ideal transformer symbol as perfectly coupled coils of certain turns ratio, say N1 to N2. This is the ideal transformer. Then to account for phi 11, the flux that doesn't reach the secondary side from the primary side, we said this is going to reduce the voltage that reaches the secondary side from the primary side. So we established a voltage divider 1 minus K times L1 and KL1, so that we reduce the voltage that's applied across the primary side of the ideal transformer to reduce the voltage that reaches the secondary. And then we found that we need to add another inductance here, 1 minus K, in order to account for the fact that the inductance we will see from the secondary is basically should be L2. And then we have the equivalent series resistance of the primary coil as well as the equivalent series resistance of the secondary coil. And then we have the typical voltage V2. V1 is the applied voltage, V2 is the received voltage, and then I1 is the current of the primary side and our transmitting side, and I2 is the current at the receiving side. So according to this model, which is called, by the way, the equivalent transformer model, what will be the voltage transfer ratio? By that I mean what will be V2 with respect to or as a function of V1. And for simplicity, let's assume R2 and R1 equal to 0. So the wires that the coils are made of are very thick, so the equivalent series resistance is very small in value. So let's use this model and find V2 as a function of V1. So we'll find that V2 is equal to the voltage here essentially and assume here, of course, so we have here two assumptions. Number one, R1 is equal to R2 is equal to 0, so the equivalent series resistance of the primary and secondary coil is 0. Number two, the second assumption, we are going to assume that the secondary side is left open and we need to find what voltage we are going to measure. So we have, that's the second assumption, secondary is open circuit. So we have that V1, then we have a voltage divider here. Of course, the current here is going to be 0 because this current is 0 because we left the secondary side open. And so we have basically V1 is applied across a voltage divider that's established by the leakage inductance and magnetizing inductance. And so basically we just multiply by KL1. Of course you could put omega, J omega, but it doesn't matter. Divided by KL1 plus 1 minus K times L1. So if you multiply the numerator and denominator by J omega, you get the same expression, and then you will cancel J omega in the numerator with J omega in the denominator. And as you can see, you can cancel L1, L2. Oh, but before we continue, so this is the voltage across the magnetizing inductance. This is the voltage across the magnetizing inductance. And then we need to multiply that by the the turns ratio of the secondary, which is basically equal to, the turns ratio of this ideal transform, which is square root L2 over L1. And so we'll find minus K will cancel with K, and we have in the denominator 1 and K in the numerator. So essentially we'll have V1 multiplied by K multiplied by square root L2 over L1. So the ratio between V2 and V1 is equal to what? K times square root L2 over L1. On the other hand, in an ideal transformer or a power transformer that doesn't have the leakage inductances, we'll find that the voltage transfer ratio in an ideal transformer V2 over V1 is equal to square root 2L2 over L1. And so the poor coupling between the primary and secondary, which is represented by the coupling factor K, essentially is going to reduce the voltage transfer ratio between the primary and secondary by a factor equal to K. And so for loosely coupled or essentially transformer not coupled together at all, K is equal to 0, so the voltage as the secondary will be 0, although we are applying voltage at the primary side. On the other hand, for power transformer or transformer tightly coupled coils, K is equal to 1, so basically the turns ratio or the voltage transfer ratio is given by square root L2 over L1.